register. The purpose of this lab was to analyze the motion of a swinging and oscillating spring and produce a glow script model to accurately replicate the tracker data. The models used were a glow script computational model and tracker video of oscillating spring motion. The principles are Newton's second law and the work energy principle. The main result is that the glow script model was able to accurately replicate the provided model with only slight deviations in the x or y direction. Main ideas. The main physics ideas in this lab are Newton's second law of motion, the work energy principle, spring potential energy, gravitational potential energy, kinetic energy, position and velocity update, and the formulas for the total energy in a system. On the bottom right, we see the velocity and position update, and then bottom left, we see the rest of the formulas. The system and surroundings in this experiment. The system includes everything in this experiment, and there is nothing in the surroundings. Here are the initial conditions. We have gravity, a spring constant of 6.83, our relaxed spring length, the initial ball position and ball velocity, and the time that this experiment is happening over. The experiment portion of this experiment. To capture the motion in tracker, a calibration stick was set to the original length of the spring at 0.7 meters, and the origin was set to the base of the spring. The video was then analyzed to gather movement data in both the x and y directions. And we can see a screenshot of the tracker data and the tracker software on the bottom right, and the motion of the spring and it being graphed in the top right corner of the screenshot. The coding portion. Using the source code provided, I produced a model that predicted the motion of the oscillating and swinging spring. This is the code that I produced. Starting on the right side, we have our kind of initial conditions and the first section of the code. And then on the left side, we have the actual code that ends up producing the model that we use to compare. Similarities and difference. The computational model is pretty accurate, but there are some notable differences. The experiment data in the x direction has a noticeable lag versus the computational model. We see this in the bottom left image. And then the computational model also overshoots the experiment data in the y direction very consistently. We see this in the bottom right image, where the blue is the model and the red is the experiment data. Possible sources of error. In the computational model, the mass of the object on the end of the spring is not accounted for, whereas it is in the experimental data. This is the most likely source of error for this experiment. What if? If you find the period of oscillation with respect to x, it is 1.655 seconds, whereas with respect to y, it is 1.52 seconds. This difference is likely from the different distances that the mass travels in the x and y directions. Seeing as the spring was not released at a perfect 45-degree angle, it will not travel the same distance in both the x and y directions. What does this mean? So this means that the energy principle was satisfied in this experiment because the change in energy is zero. There is no work being done in the surroundings. And we can see this because the system is everything in the experiment, and the surroundings, there is nothing in the surroundings in this experiment, so there is no work.